It seems like it should by now, right? So it's misleading, I think, that it looks like it's defined. Now, what was the limit as we approached to? It was 4. That means as we get closer and closer, right, from both sides, it is approaching the value of 4, right? That's what this means, right? So we just did a problem, right? I gave you a vector function, and we found a limit. And what was that limit? We just did this. We said, what's the limit as t goes to 0? And we got what? The vector 1, 1, 1, right? The vector 1, 1, 1. So what we're saying is that if you try and plug 0 into this, right? If you try and plug 0 in, the vector function is undefined. But if you try and plug in values closer and closer and closer to 0, your vectors are going to get closer and closer to this vector, 1, 1, 1. You may never get there, but that's what it's approaching, right? And why is the limit so important? Why in the hell do we study the limit in Cal 1? Like, what's the point of the limit? I mean, why don't we just say, oh, it's undefined there and just be happy and go about our business? Why do we need the limit at all? What's the derivative? The derivative is a limit, isn't it? Back in Cal 1, the idea of the derivative was that if you have a curve and you want to try and find the slope of the tangent line at one point, right? You're trying to find that? What we do is we get another point and we find the slope of the secant line, the line between them, and then we drag this point over on top of that point. And we can't put this point right on top. Why? If you put a point on top of another point, can you have a line between them? No, you have to have a little bit of space between them to have a line. And so what we do is we take a limit as this point approaches that point. You have to have the limit to do that, though. Okay, I'm going off a little bit. All right, so we are seeing here that it is possible for us to define a limit of a vector-valued function. And if we can define the limit of a vector-valued function, then it should make sense that we would be able to define the derivative as well, right? All right. Continuity. That's it, limits. We're done with limits. Now we're going to go on. Now, I should say that L'Hopital's rule, right? There's a lot more to L'Hopital's rule that I didn't show, right? L'Hopital's rule is only good for what? You can only use it when you have this or this, right? But there's a whole bunch of other indeterminate forms that you learn in Calculus 1 that require L'Hopital's rule. Things like if you ever see a limit and you have 0 to the 0, that's an indeterminate form. If you see something like infinity to the 0, that's an indeterminate form. If you ever see something like 1 to the infinity, that's an indeterminate form. And these, depending again on your background in Cal 1, to do these, you have to bring in like natural logs, things like that. So I'm leaving a lot out here that is on your mini exam too. So if you're looking at it, you're like, I can't figure out what this limit is, that's when you need to reach out, get with me. I'll point you to some L'Hopital rule videos that you can look at. Okay, it's been a while. All right, moving on to continuity. So the idea of continuity back in college algebra, in Cal 1, the idea of continuity is a function is continuous, basically if you can draw it without picking up your pencil, right? That's the idea of continuity in Cal 1. But there was a definition for it as well. And we have the exact same definition. If you replace this r, this vector r here, and this vector r with f, and you made this like f of t, f of a, it's the exact same definition from Cal 1. All it's saying is that in order to be continuous at a point, your vectors have to be approaching the vector that is defined to be at that point. So in Cal 1, we had this. This function would not be continuous here, would it? Not, let's say, if this is a. This function would not be continuous at a because we have a hole. In order to be continuous, the limit, right, as we approach that's this limit, what must be equal to the function's value out there. So we have to be able to fill that in with a hole. And then it's continuous at that point. With vector functions, what we're saying is that as you're drawing your vectors have to approach the value of the vector at that function. This is not that big of a deal for us. We're not going to get deep into this, all right? But we need to understand that continuity is something that can be defined here for us. All right. So this is just, now we're kind of stepping back for a moment. I wanted you to just look at that and tell me if you could describe to me what this curve actually is. Like it draws something, right? Can you tell me what it is? What it draws? A line. Isn't that, haven't we already studied this? Right? We have those numbers right there. What was that considered? The direction vector of our line, right? That's the direction vector of the line. And then what about these numbers here? This 1, that 2, and there's, what's over here? A 0, you could say? You could say that 1, 2, 0 would be what? Like a point on that line, right? So this should look familiar to you, right? This is a line, we've studied it, but more generally speaking, it is a vector valued function, right? It is a vector valued function that lives in three-dimensional space. It's a line. So the only reason for that note is just to remind you, like we have already talked a little bit about vector functions. There's one in particular. Okay. We've done this as well. Can you find the vector function that would generate the line segment that connects those 2 points together? From here to here. Again, this is more of like, this should be like a review. We've done this, right? So how do we do this? It is important we're going from here to here. I say it right here, right? You need the direction vector, right? So we're going to use this generic formula because it's a line. How do you know it's a line? Because I'm saying line segment, do line segment, right? This was the generic formula. So R naught, what's R naught for us going to be? It's the point we're starting from converted to a vector, 359. Plus t times, now v is the direction vector, right? That goes, it's the vector that goes from here to here. So we do -5, take away 3, so -8, 2, -12. Are we done? Okay, yeah, so we could clean it up, right? Put it all together. Would we be done? Yeah. Careful. What am I looking for? The vector function for the line segment. Don't draw me the whole line. This draws me the whole line, right? I need restrictions on t. And what did I say the restrictions on t will always be if you do it the way that I told you? Like the point you start from is this R naught, and the vector from here to here is that vector. Then what will the restrictions always be here? 0 to 1. If you decide to go from this, if you decide to use that here, and then your vector go from here to here, it won't work from 0 to 1, okay? Because you've changed your starting initial point. So as long as we all do this the same way, this goes here, the direction vector is the one that goes from here to here, then this will always be 0, 1. Questions there? I'm not going to clean it up. You could distribute through and put them together, right? Okay. All right. Everything seemed pretty smooth so far? And then I give you a problem like this. And you're like, wait a minute, that doesn't seem like we should be able to do that. Like, I have not given you enough information. Find the vector function and its domain representing the intersection of these cylinders. Okay, we studied cylinders last class, right? Cylinders like this infinite beer can, kind of. This first cylinder, x squared plus y squared equals 9, is a cylinder that goes which way here? It's like on the z-axis, right? It's like a beer can kind of this way with a radius of what? 3, right? Because it's 9. So you've got this, 1, 2, 3, draw a circle, can goes up, goes down. Y'all see it? Okay. And then I have another cylinder, y squared plus z squared equals 4. Which axis does that go down? the x-axis, right? It goes this way, and it has a radius of what? 2, 1, 2, so draw a circle this way, can going that way, can going this way, and I want you to find the vector function that draws the intersection of those two. Does that seem difficult? You are trying to find these two cylinders, right? You have to come up right now, you have to come up with, see that the blue curve there? The intersection of those two? You need to come up with the vector function that will draw me those two curves. So you know that every point on these blue curves, every point must satisfy both of those equations simultaneously, right? That I think we could all agree on, right? There's some x, y, and z that solves both equations at the same time. So why not just solve that system of equations, right? Well, it's nonlinear, right? This is not linear algebra. These are not linear equations. These are nonlinear, right? X squared plus y squared equals 9, and then y squared plus z squared equals 4. These are nonlinear. How do you solve systems of nonlinear equations? There's not a nice method, okay? There is no simple method to do it. It's actually very difficult to do. So we need to think about this more abstractly, all right? Do you understand? Doesn't it seem really hard to do? Like, I mean, not really hard, but it's not like find the vector function of the line segment anymore, right? This is a little more involved. Why would we even care to know this? Right? Why would you even care? Maybe you have some pipelines, right? And these are the intersections, and you're going to hire somebody to weld all these intersections together, right? And so we'd like to know the length of this curve. Now, we haven't talked about how you find the length. That's the next section. It's called arc length. Once we find the vector function that draws this, then we can use another formula to find the length of the curve. So we could actually figure out exactly the linear feet of that weld, and then we can say, oh, how many of these are we going to, oh, we have 100 of these welds, how much are we going to pay this person, right? I mean, there's a lot of things that go into that you could apply this to, but finding that curve is the first thing. All right, everyone understand geometrically what we're trying to do? All right, so here's what I'm going to do. The first thing I'm going to do is this. I'm going to see if I can't wrap my head around this one first. And I'm going to just start right now with the vector function. All right, so we said to draw that, right, it's a circle in the xy plane with a radius of 3, and then the z just goes up and down, right? So to draw a circle in the xy plane of radius 3, I use 3 cosine t, 3 sine t. Do you all agree that this so far puts me on that first cylinder? I'm just going to call this cylinder 1. Let's call this one cylinder 2. Do you agree that so far, for any value of t that I plug in here, I'm at least going to be on the first cylinder? Yes? Now, the problem is, as I draw this, right, if I draw this circle, I need to be up on the intersection as well. So I need to be on that other cylinder, so I have to satisfy the other cylinder's equation as well. The one thing I don't know here right now is what that height is, right? I don't know what the z should be. So what I can do, I can be clever, is I can say, well, wait a minute. Take this equation and solve it for z. Solve that equation for z, because that's the component we don't know, right? So z squared equals 4 minus y squared. And that means z is plus or minus the square root of 4 minus y squared. Now, unfortunately, we can't do those separately, right, because there's subtraction between them. So we just got to leave it like that. So what we're saying is, in order to satisfy this equation, the z must be this, right? But at the same time, we have to satisfy that equation. And so do we know what the y value has to be? If we're going to satisfy both, what does this y value have to be? 3 sine t, right? Because that's what these components are. This is your x, right? This is your y. And then this is your z. And z must be, so we're going to put this in here. It's going to be plus or minus, wait a minute, we're getting two different answers, aren't we? Well, there's two different curves, aren't there? There's two different curves, one on each side. So this will give us both. Plus or minus the square root of 4 minus what? 3 sine t squared, right? It's that y coordinate right there, squared. I'm going to write 9 sine squared t. Do y'all agree? Yes?
Did you get cosine and sine for x and y?
Remember how we were just drawing a circle a minute ago? Same idea. I changed the a in front. The a controls the radius. So I'm trying to draw this cylinder. This is a circle, right? In two-dimensional space, it's a circle of radius 3. That gives me the circle in the xy plane. That gives me the circle of radius 3. Does that answer your question?
This is just like for the first equation?
I chose to start with this equation. Say, let me first just try and see if I can create a vector function that at least gets me onto this cylinder first, right? And what I said is, okay, to be on this cylinder, then the x and y would have to be this. But to be on the intersection, I'd have to also be on this curve. I need to know what the z component of this vector function is. Since this has z in it, I solve that for z, and it has y in it. I know what y is. I replace that y in, and I get this. Is that okay? Do we have a vector function that appears to give us the intersection? Yes? Okay. We don't have its domain yet, all right? We don't have its domain. I'll talk about domain in a second. What I want to do is I want to restart the problem again, but I want to do it with another student who did it a different way, okay? Can I erase? Okay, so another student comes in and they say, all right, you know what I'm going to do? Is I'm not going to start with this one. I'm going to start with this one. So let's start with this one first. So if I try and do a vector function that would put me on that one, that is a circle of radius 2 in the yz plane, right? And then the x is the one that goes up and down the x-axis. So it's in the yz that I would need what? 2 cosine t, 2 sine t. That will draw me circles in the yz plane. Here's y, here's z. It's drawing me circles this way. Yes?
Could they be in different positions? Could that have been 2 sine t?
Yes, that would impact your domain a little bit, but it would still draw a circle.
How would we know what to put where?
Normally we start with cosine. It actually does not matter. Okay, it doesn't. Look, if I want to draw, if I do cosine t sine t, let's go back to two-dimensional space. All that does is starts your circle here and then draws like this. If you switch it, what happens if you switch it? So if you plug in 0, you get 0, and then here you get 1. So now you start here, you see? But as you plug in values, you're still going to draw a circle. So all it does is changes your starting point. That's it. But the convention is to put it in the component that's to the left. Okay. So you either do cosine sine or you do cosine sine. Yeah. Good question. I remember as a student that confused me a little bit, like, does it matter? Yeah. You just can't have like sine sine, or one has to be sine, the other one has to be cosine. All right, do y'all see that we know the y and the z, right? We know what y is, we know the z this time. But now we need the x to put us on the other curve. So what can I do here? Solve for x, right? Solve for x. So if we solve that for x, we get x is plus or minus the square root of 9 minus y squared, right? Same method that we just used a second ago. We know what y is, don't we? So now this becomes plus or minus the square root of 9 minus, square that, we get 4 cosine squared t. There we go. What if this wasn't a circle? Well, if one of these was a circle, we could still do this, right? What if this was a plane? What if this was a plane equation? Remember what plane equations look like? Like what if this was the equation 2x plus y minus z equals 10? What if that was a plane and that was your cylinder? You still do this, right? But now, to get x, what would you do? Take this equation, solve for x, and then replace your y and z with these two. And that would give you where the plane intersects the cylinder, which would almost look like an ellipse but twisted sideways. Okay, let's discuss domain. Let's do domain on this one. We just need to make sure that, what do we need to make sure? We need to make sure that this right here, what? Is greater than or equal to 0, right? So we have to be careful with quadratic inequalities like this. We could add 4 cosine squared t to both sides, and we could divide by 4. That wouldn't change anything. 9/4 less than or equal, 9/4 greater than or equal to cosine squared t. Pardon me?
So 3/2 is greater than or equal to cosine t?
So is that the way it works? We have to be careful. We have to be a little bit careful here.
I forget the rules for something like this.
Yeah, so this goes back to quadratic. This is called a quadratic inequality. And the way you solve these, you have to be careful. Let me show you. I'm going to do it. That's why I wanted to put this problem up here. Let me give you something. Well, you know what? I don't know. Should I? It's Cal 3. I'm not going to give you another example back from college algebra. This is a quadratic inequality. The way we solve this is as it follows. First step is you change it to an equation. You change it to an equation first. And then you solve that. So to solve this, you do the square root on both sides. So you get plus or minus, what? 3/2 equals cosine t. That okay? So you get your two solutions. Then what do? You put those, do y'all want to solve for t or not? Let's just leave it like that. I get two solutions here, negative 3/2 and positive 3/2. What I need to check are some values in these three regions and see if they make this true or false. I have to check. So let's check the easiest one. What's the number in here? 0. Let's check 0 in here. What's cosine of 0? 1. 1 squared? 1. Is 9/4 bigger than 1? Yes. So this region works. Now let's pick a number out here. Something bigger. 2? Okay. What's cosine of 2? Well, you're going to need to... You want to do pi?
Yeah.
Pi?
Yeah.
Okay.
-1.
-1 squared?
1.
Does that work?
Yes.
What about the other side? So what do y'all think? What's the answer here? They all work. Now, could we have figured that out from the beginning right here? What does cosine squared look like if you graph it? What's the biggest? If you think about what cosine looks like, cosine of t, right, has to be between what two numbers? What's the bound on it, right? So if I square this, then this it has to be between what?
0.
0 and 1. When you square cosine, it has to be between 0 and 1. And 9/4 is always bigger than 0 and 1, right? So you could have seen it here, that this right side is always between 0 and 1, and therefore that's always true. Which means there's no domain restriction here, right? You can just all real numbers, it'll just keep drawing those things over and over and over, right? Just over and over and over. Do y'all remember I said two students did this two different ways? In the first way I did it, what was the z that I had in the first way I did it? It was plus or minus the square root of 4 minus 9. Was it cosine? Sine squared t, right? Do you all see the difference between these two? There's a difference. This one, when we set it, we got 9/4 bigger than that, right? If you do that over here, you're going to get what? 4/9 bigger than or equal, and that's going to have a domain restriction. So what I'm saying is the student who did it this way is going to have no domain restrictions. The student who did it this way is going to have domain restrictions. So, you know, it's just the way it worked out.
So is there a right and a wrong one, or they both
They would both be correct. In fact, when I did the problem on the computer, I did it this way. And so I actually do have domain restrictions. I have domain restrictions. My t has to be between negative 41.8 degrees and positive 41.8 degrees. And then, let me erase this first. You can see it here.
So do we want an answer that has all real numbers?
I would think that would be better, right?
Yeah.
Because then you don't have any issues. Yeah. But it doesn't make this way wrong. It just makes it more work. All right, so here it is. So what I'm showing you here is that it does work. That as for the first version I showed you, I have a function, and you can see the black vectors are going to draw that blue curve over there on the right, and the one on the left is drawn with the different domain restrictions. Okay, that's it. We're moving on. All right, now when it comes to graphing vector functions, right? When it comes to graphing them, really hard to do by hand, just generally speaking. If it's a line, sure, we can do it. But if it's something crazy, computers can do that for us. So here's some examples that I typed into a computer. This one right here is called a toroidal spiral. And where's the function? Where is it? I don't have it there. I thought it was here. I don't actually have the function listed here. Oh. This is it right here. If you want. This is the vector right here. This is the first component function, the second component function, and the third component function right there. Those are the three component functions that I had the computer graph, and it draws me this. Y'all know what a torus is? A torus is a donut, okay? A donut is a torus. Y'all know how you create a donut? It's getting into, I don't want to tear that up. Sacrificial piece of paper?
You need one?
Yeah, do you have one? Thank you. So there's a subject in math, an actual class that you can take called topology, not topography, topology. And the idea of a torus can be thought of this way. Imagine I take this sheet of paper and I take the top edge and bottom edge and I paste them together, right? Then I create this cylinder, yes? And then at the same time, I want you to paste this edge and this edge together. So you paste those two together. Imagine this can stretch, all right? Now take this edge and paste it to this edge. And if I do that, I come around and I create a donut. You all see that? That's called a torus. This is a toroidal spiral. A toroidal spiral is a spiral going around the donut. So can you all see the donut in there? There is a donut there, and this toroidal spiral goes around it. Okay? Let's see something else. These are just interesting vector functions. This one is called a trefoil knot or a trefoil knot. It's hard to see this, but this is a knot. It's just, it ties on itself. So if you were to pull this string tight, you would have a knot. And again, this goes back to the whole idea of like if I put, some ant or mouse in the room and it walks around, like who's to say it has to follow any path? Same thing with like a rocket or something, flying around, lose control of it, starts going all over the place. There's nothing that says, wait, you have to be a function, right? We don't want any sort of like vertical or horizontal line test restrictions. All right, derivatives. Good news. I have good news. The derivative of a vector function is what you would hope it would be. It's just the derivative of each of the component functions. So if you want to know a derivative vector function, all you have to do is take derivative of each of the components. Boom, boom, boom. That's it. Okay? As long as you can take a derivative, you're in business. The question is, what's the answer, right? If you take the derivative of a vector function, you get a new vector function, don't you? It's going to be a new vector. It has 3 components or 2 components if you're in 2-dimensional space. So what is the geometric meaning of the derivative? Well, back in Cal 1, the derivative represented what? Slope of the tangent line, right? Here, the derivative is a vector. So what does it represent geometrically? Well, what does it say here? So if you take the derivative, right, of a vector function, you're going to get a new vector function. Now, if you give me a value for t and I plug it in here, that's going to give me a vector, right? What is that vector? That vector is going to be tangent to the curve at that point that we're looking at. It's going to be tangent to it. So I have a picture here. So there's a picture. In blue is a vector function, okay? You don't see this? This is a vector function, r of t. And then what you're seeing here in red is me using the computer to calculate the derivative, which is a vector, right, at each of those points. And notice that as I move my t along, shit, I don't know why it's slowed down there. Why is it slowing down? This should not be slowing my computer down. Okay, so look at that picture right there. We have some vector function, right? R of t. If I plug a value of t into this, I get the black vector, right? Which takes me to a point on the blue curve. If I plug that same value of t into the derivative, I get this red vector, which is running tangent to that curve, right? Tangent to that curve at that point. And continuing to move, you see it, right? Now, do y'all notice these vectors, the length of them is changing? The red one, do you see its length is changing? So for those of you who've done some physics and stuff, what can y'all tell me about that vector? Its length would represent what? The speed of that particle moving, right? The speed. So the vector gives you both a direction and a length, right? Magnitude and direction. That's what a vector, that's the very first definition we had of vector, right? Vectors have magnitude and direction. So for us, the direction is going to be the tangent part, and the length is going to be how fast that particle is moving. So let's do this example. Let's find the derivative of this vector function first. This is going to be super straightforward. So what's the derivative of that vector function? So what is the derivative of that? All you have to do is take derivative of each one of those, right?